8 years ago, almost to the day, I was invited to introduce some of our first attempts to port this model Icon to GPUs. It's a real pleasure to come back here and tell you 8 years later how it all went. This is a very large effort, large number of people. The list of authors is only a subset of the people computed to the GPU programming side of Icon, and is a much smaller set than the total number of developers. So let me get right into it. I know we want to keep on schedule. Let's just take a quick step back to programming paradigms. This is something which came from discussions with Jeff Larkin, who's going to be speaking in a few minutes. We would like to have base language support for programming these emerging technologies. Now, the reality is that we don't have that currently. Either they're not properly implemented or don't perform very well. So we've had to go back to things like directives, pragmas, and also language extensions. For the right hand, that's CUDA or CUDA Fortran, to get our software running on things like GPUs. Now, there is an overarching interest we have, which is in domain-specific languages, and which present to the application scientist a syntax which they should be more familiar with. We have a lot of experience in domain-specific languages, things which generate code in one of those three boxes, or go by some other direction to the underlying hardware. That's a subject for another presentation entirely. However, 10 years into our efforts, directives, in particular OpenACC and OpenMP directives, are doing most of the work. So I'll leave that with that and get into Icon. So Icon is an ecosystem of atmospheric and ocean modeling softwares, multiple applications actually, for climate and numerical weather prediction. It's been developed by a very large number of people. There are 4 member institutions in Germany who've developed it, but there are also a lot of associated members, including ourselves now, CSCS. It's about 2 million lines of code written in Fortran and C in the last 20 years. And it's a successor of another model called Cosmo, which is a regional model for also climate and numerical weather prediction. But the community is transitioning now to Icon, the German Weather Service, or DWD, in 2015, our own national Met office, Meteo Swiss, in 2022, and a lot of climate scientists are now transitioning as well from Cosmo to Icon. So this is my one-slide introduction to atmospheric modeling, but I can't go into any real detail about this. Basically, in atmospheric modeling, you wrap the globe with a 3-dimensional grid of prismatic cells in the vertical. There's some sort of an initial state. You load that initial state, and then there's a time-stepping algorithm to walk into the future. Now, part of that time-stepping algorithm has what we call a dynamics, or solving atmospheric flow equations with dependencies in all 3 dimensions. And then there's another part of the calculation called physical parameterizations, which operate on only vertical columns. In other words, no horizontal dependencies. They periodically write output to disk and then continue in this time marching fashion. So that's all I'm going to say about atmospheric modeling. Hope that suffices for this presentation. So let me continue here. This is the timeline for our effort. And interestingly, it was almost contemporaneous with the port of GPUs of Cosmo, the older model we're now replacing. And there was a lot of forethought of our director to concentrate already at the very beginning on Icon, because we suspected it would supplant Cosmo at some point. And that, of course, has come true. So in 2011, we created a couple of prototypes, including Fortran and OpenCL. for the dynamical core of Icon. The Icon developers said, oh, that's very nice, but there's no way we're going to include that into our repository. It has to be a directive-based approach. In other words, for us, comments essentially in the code. We got funding from the EU in 2013 to 2016 to rewrite the Icon dynamical core with OpenACC directives. That's what I presented in 2013 at the summit. We made an effort to port some of the physics underlying physical parameterizations to GPUs. That was unsuccessful because the scientific development was too quick. We could not keep our code synchronized with the scientific developers. It's an independent effort to port a radiation scheme, which is very central to these models, by Robert Pincus and Matt Norman, among others, and we gave them a bit of advice. We did have another project to port the climate physical parameterizations, not the weather forecasting, but the climate physics to GPUs, which finished last year. It turns out our effort to port the underlying radiation scheme in those physics was unsuccessful, and we had to revert to that other radiation scheme I mentioned, Robert Pincus. We had to refactor the dynamical core in that project. I have a slide on that. And then there was a final push in 2019 to incorporate all these components, testing, and finally system integration. And we're very proud that we're running real simulations. These are on something called a quasi-biennial oscillation, the global simulation at very high resolution at CSCS until 2021. And of course, these are things we've presented in numerous conferences on the way. What is interesting about Icon, why is it called Icon? It's called Icosahedral Non-hydrostatic. It's based on an icosahedron, which is then pumped up to a sphere, and then you can recursively bisect the edges to form more spherical triangles, and then continue the process recursively to get any resolution you want. And what's interesting about this grid, unlike, for example, latitude-longitude grid, that the cells have roughly the same size. That's very important for reasons of numerics. Well, let's get right into it. So what were the good aspects of our experience? Well, OpenACC gives you good performance, assuming very careful optimization. It really works. I'll present some benchmarks in a minute. We had good support from vendors, initially with good support from Cray for their CCE compiler, OpenACC capable compiler, and then later in the last 5, 6, 7 years from PGI and then Nvidia. And in 2013, Icon did not even compile for CPUs with PGI. A lot of credit goes to Dave Norton for tracking down and reporting 20 compiler bugs or more. And finally, in 2018, the compiler was working also for GPUs. Dmitry Alexeyev has been a huge help. He reprogrammed OpenACC atomics, which weren't performing very well, to calls to the Nvidia QUBICC library. And he did extensive optimizations for A100, for example. Now we have really strong bonds to the OpenACC community. We participate in the weekly technical calls to give our user perspectives on things. Our director, Thomas Schultes, is a board member since 2019. And ultimately, we were successfully doing these QBO simulations on, well, first on our leadership platform and now on the Jülich Joules Booster A100 based system. So a few benchmarks. These are again thanks to Dmitry. Larger is better. Everything has been normed of all these components to the performance of OpenMP threaded CPU performance on a Haswell socket with 12 cores. So that's one. The same code, OpenMP code, running on AMD, the new version of AMD CPUs. Dramatic improvement. about 5 or 6, very comparable, incidentally, to the P100 or yellow performance, which we have in-house on our pit stains. V100 blue, again a large jump, almost, well, over 10 times faster. And then A100 in the 40 and 80 gigabyte versions, getting us to 20, maybe even 30 in some cases, times improvement over a single socket Haswell. Very proud of those single node performance numbers. Strong scaling is slightly more sobering. So this is a medium resolution, 20-kilometer global run on different on the nodes of different systems. As you see on all of these systems, the performance tails off with increasing node number as the GPUs become less and less occupied, which is a known circumstance, and nothing to be concerned about for us, because we know the sweet spot on number of nodes and where we should be running. So this is joules and pit stained and also an AMD CPU system. Finally, similar numbers of my own benchmarking. This is 3 different resolutions, low, medium, and high. And there's nothing new here. You can see the performance, strong scaling of the GPUs tailing off here. If you read very carefully, you can see, you'll realize that the weak scalability is very good for CPU and GPU versions. And and I should also mention, we have used the GPU to GPU direct communication for many of our runs, which gives us an extra 5 or 10% performance improvement. Not everything was good. So this is a honest version of our experiences. So Icon is a monolithic code. It has very few unit and component tests, and it's similar to Cosmo in this respect. We invested huge amount of time in our testing infrastructure. I'll get back to that in a second. The original dynamical core, which I mentioned in this price project, wasn't designed properly. It had to be refactored subsequently in 2018, 2019. And the funding was mostly time limited. The ENIAC team did complete the physical parameterization port, but barely did it, and a lot of the integration work fell back to us in the end. That was okay. We managed to do it, just a little bit more work than we expected. I'll just mention that restructuring, or refactoring effort. So the solution to the hydrostatic, non-hydrostatic equations, or dynamical core, consists of multiple 3D nested loops where some prognostic variable is set to a function of the neighborhood around a particular IJK point. And they're just multiple triply nested loops like this. Well, and you see the OpenMP parallelism over the outermost blocking loop. Well, we tried to do something which was intuitive, namely to get parallelism over all 3 loops, and namely a gang loop on the outside and vector loop on the innermost loops. Unfortunately, that is not consistent with the physical parameterizations, where that block loop is many, many levels up, in subroutines 3, 4, 5 levels up. And so in order to keep the same data structures for both the dynamics and the physics, that had to be reprogrammed, extracting only the OpenACC parallelism in the innermost loop. This is fine as long as the number of boxes is very small, and this blocking factor n proma, which you perhaps see, is very large. Then it still performs very well. Let me get back to this point. Scientists are not software engineers, as we all know, and the Icon developers either don't write unit tests, or once they integrate their code into the model, they throw them away and perhaps insert a few flags to toggle, the particular tests within the full model. I seem to have lost my slides. Hold on. Hold on. Okay. That is not good for porting to GPUs. Remember that we couldn't even compile with a PGI compiler initially. You don't want to compile the whole model. It's much easier to create standalone drivers, for example, with serialized data from real model runs. We invested, as I mentioned, a lot of time into tools for testing, particular serialization library called Serialbox, which includes a simple script to basically support serialization directives inside the code. There's also a Fortran test generator, which extracts certain subroutines from the full code, can serialize the data from a real model run, and then creates a standalone test driver so we can develop in isolation. So this was very important, but just keep in mind that this testing was at least as big an effort, no, probably many times larger effort than the actual porting effort. We did another issue. We did create tools. This CLAW is a source-to-source translator which uses some sort of meta-directives and generates then directives, either OpenMP or OpenACC directives. And it has a very neat single column abstraction, so the scientists can define the physics only in one of those single vertical columns you saw previously, and then can generalize it to multiple columns covering the entire Earth. It's a great tool, very useful. However, long-term support, maintenance is not available. The main developer, Valentin Clément, is now working in on Flang, and there's no support. Thus, this tool is no longer useful for us. This is a pity, but it's part of the ugly facts of efforts like this. Okay, there were some bad things also which happened in my mind. Why did we use OpenACC? Again, because of the requirements of the community, but also because of the Cray's initial enthusiasm, sort of in 2011, 2012 timeframe, that they felt this was the way to go. Now, in fairness to Cray, they did give us advance notice that they were shifting from OpenACC to OpenMP, roughly in 2015. They finally announced that OpenACC was no longer supported in 2019. By that time, we were in a multiple-year transition to PGI, which was ultimately successful. Interestingly, for the Lumi procurement, that is the pre-exascale machine in Finland, HPE Cray promised a sufficient support for the Icon benchmark code we gave them, but no more than that. And just recently, I learned last month that HPE is now committed to supporting OpenACC and OpenMP directives for GPUs in an agnostic fashion. In other words, they don't prefer one or the other. And I think this is great news, but a complete paradigm shift. Yes, one more bad thing. We did use unofficial extensions. In particular, Cray offered a full automated deep copy in their original CCE support. That's neat because we have extremely complicated derived types. In that particular case, we could use this feature to copy in these very complicated derived type instances outside of the time loop. And of course, nothing is as simple as it seems. We had to massage the code a little bit to get it to work, but it did in fact work. We were hoping that would be incorporated into the standard, at least the support for Fortran. And there was a protracted discussion in the OpenACC committee. And finally, in 2018, we stopped waiting and we implemented that copy This is about 10 lines of the several thousand lines of code, which actually copy those the members of those derived types to the device. My bad for using non-official features to the standard. Okay, so 8 years ago, I learned from Michael Wolf that you always put your take-home messages on the final slide. So here they are, just to remind you. OpenACC is a successful approach in the absence of base language support, which we might prefer. We've had successful collaborations, not only with the scientific community, but also with the OpenACC community. We've had a great support from Nvidia and good performance. I think I've shown that. Our partners now see the value in GPU programming. That's critical. They realize that because potentially they will get GPU machines. There are follow-on efforts to port other components to GPUs. Some things were ugly, right? Icon is not a pretty code. Component testing was very difficult. OpenACC has deficiencies, but also tools or DSLs even, like the Claw tool I mentioned. There were some personnel bottlenecks. That's to be expected in any project. I found it very bad that Cray dropped the support for OpenACC in 2018. It's great that they reversed the strategy in 2021, albeit there was some loss of customer confidence in that reversal. I chose to use non-standard features, my bad. We put in more effort than perhaps we foresaw in the port, and we did lose this high visibility quasi-biennial oscillation simulation to Jülich, something which personally is not too satisfying, but I'm glad they're doing successful simulations there. With that, I'd like to thank you for your attention.